We know that for any triangle, there exists a circle inscribed in the triangle, the incircle. But what about a quadrilateral? For which quadrilaterals there exists a circle that is tangent to all four of its sides? Today we're going to answer this question. First of all, let me note that there is a second way in which a circle can be tangent to all of the sides of the quadrilateral, similar to how we had more than one circle that's tangent to all three sides of a triangle, namely the three x circles, if we allow the points of tangency to be on the extension of the side, but not on the side itself. Here, for this quadrilateral, if we allow the points of tangency to be not on the sides themselves, as it was the case with this inscribed circle, but to be on the extension of these lines, then for some quadrilaterals, this circle exists a circle for which the points of tangency to all four sides of the quadrilateral lie on the extensions of the sides, so here, 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 and here. And we're going to see what are some necessary and sufficient conditions for this circle here to exist, as well as for the regular incircle here to exist. First of all, let's take the regular incircle, and let's see what properties we can get. The main property that we're going to use is that if we have a point and we draw two tangent lines to a circle, then these two segments that we get are equal. And so if this is A, then this is A. If this is B, then this is B. If this is C, then this is C. And if this is D, then this is D. Now suppose this segment here is E. Then from this point we drew tangent lines, and it turned out that E plus A equals this segment here, which is D plus something, and so this something must be E plus A minus D, such that this is E plus A, and this is also E plus A. Similarly, on this side, if this segment, this little segment is F, then this here is F plus C, then this here is F plus C, and then we remove the D, and we get that this segment is F plus C minus D. Now I'm going to label the points A, B, C, D, E, and F. Now there will be three necessary and sufficient conditions for this circle here to exist. Now that we already supposed that this incircle exists, we will write these three conditions that I've listed here, such that I will put one segment on each of these unknown spots, and this segment will be between a blue point and another blue point, so a point that I already labeled, and there will be no repetitions, meaning that, for example, this segment would not be the same as this segment. These 12 segments here would all be different. But look, on this line, we only have three segments that we could choose. This is segment FA, AB, and FB. On this line, we have three more, BC, CE, and EB. On this line, we have three more, and on this line, we have three more. So the total number of segments with blue endpoints on this picture is 12, and we have 12 free spots here. So each of these 12 segments will go in a unique place in these three equalities. Now let's discover how to place them. Well, one of them is kind of easier to see. It's the one where we have AB plus DC equals AD plus BC. And this is maybe the most famous one. And this is true because we have little a plus little b plus little c plus little d equals little a plus little b plus little c plus little d. And so this segment plus this segment equals this segment plus this segment. Now let's try to discover the next one. We'll take EC plus CF, little f plus little c plus little d plus little e plus little a minus little d, which is f plus c plus e plus a. And where else we have f plus c plus e plus a? Oh, we have it here, fa plus ae. We have e, little a, little d, which cancels out with this minus little d, and then f and then c. So ec plus cf equals fa plus ae. Or this plus this equals this plus this. One more time, we have e, a, f, c here, and e, a, f, c here. So they're equal. And now what's the third equation? Well, there aren't many segments left, so let's see which ones are left. On this side, we've already used BC, and we've already used CE. We haven't used BE. On this side, similarly, we haven't used BF. On this side, we've used CD and we've used CF. We haven't used FD. And on this side, we haven't used ED. In this case, let's consider the sum, BE plus FD. Well, we have B, C, F, E, A, and minus D. And let's consider the sum BF plus ED. or we have B, A, E, F, C, and minus D, which is exactly what we got from the previous sum. Here I wrote the two sums. B cancels out here, C cancels out here, F cancels out here, E cancels out here, A cancels out here, and D here. So we got these three equalities out of the existence of this circle. It turns out that if we have a quadrilateral for which even one of these equalities is true, then we can conclude that there exists a circle that touches all sides internally. We're going to prove this statement only for this equality here, but you can analogously try to prove it for the other two. Suppose we have a quadrilateral such that A plus C equals B plus D. Now we're going to prove that there exists a circle that touches all its four sides. Firstly, let's notice that A and C can't be the two larger sides of the four, because then A plus C will be strictly larger than B plus D. And same thing applies for B and D. They can't be the two largest because of this equality. And so the two largest sides must share a common vertex. So let's assume this is the common vertex without loss of generality, and that A and B are the two largest sides. I'm choosing a point here such that this distance is D, and the point here such that this distance is C. Then this distance is of course A minus D, and this is B minus C. But if we look at this equation, A minus D equals B minus C. And so this segment equals this segment. This is an isosceles triangle. And we have three isosceles triangles here. This one, and this one. And I'm going to draw the perpendicular bisectors of the bases of these isosceles triangles. So the perpendicular bisector of this side will pass through this point, of this side would pass through this point, and of this side would pass through this point because of the isosceles triangles. But these are exactly the perpendicular bisectors of the sides of this triangle here, and they always intersect at one point, the circumcenter of this triangle. Now note that these three perpendicular bisectors are also angle bisectors of their corresponding angles in the quadrilateral. For example, this is an angle bisector here, this is an angle bisector here, and this is an angle bisector here. Hence, three of the four angle bisectors in this quadrilateral intersect at one point. Let's draw perpendiculars from this point to the sides of the quadrilateral. We know that if we have an angle and an angle bisector and a point on the angle bisector, if we drop two perpendiculars to the two arms of the angle, then the lengths of these perpendiculars are going to be the same. Therefore, this length equals this length, and then this length equals this length, and then this length equals this length, because of these three angle bisectors. And therefore, this length equals this length. And now here, we've got a cyclic quadrilateral, because this is 90 and this is 90, so their sum is 180. In this circle, this chord equals this chord, and therefore, this arc equals this arc. And so the angles that these arcs make will be equal. The angle corresponding to this arc is this angle, and the angle corresponding to this arc is this angle. And therefore this angle equals this angle. Or this is also an angle bisector of an angle of the quadrilateral. Finally, we construct a circle with center this point and radius this segment. And we know that this circle passes through these feet of the perpendiculars and is tangent to all the sides because of these right angles. And this is it. This is the circle we've been looking for. Now let's go back to this picture where we had a circle that's tangent to all the sides of this quadrilateral, but externally. And let's ask, what are the three conditions for this circle to exist? And what can we say, knowing that this circle exists, about the sides of this quadrilateral? Again, these are in exactly the same form as before. We've got three necessary and sufficient conditions for this circle to exist, and each of the 12 segments that can be constructed from the blue points and segments on the picture appears exactly once in these three equations where we have 12 spots that are left to fill. Firstly, I'm going to label the segments and use the fact that if we take a point, for example this point, and draw tangent lines, then this segment equals this segment. So if this is A, then this is A. If this is B, then this here is B. If this is C, then this is C. Then if this is E, then we know that from this point, this segment equals this segment. And so this should be C plus E minus B, because then this segment is C plus E, and this segment is also C plus E. Analogously, from point A, we have D plus A here, and so here this is D plus A. We subtract B, and we get D plus A minus B. And if this here is F, then we know that the lengths of the tangent segments from B to here and to here are equal. And this is here is C plus E plus F, and this is A and this is D. So this should be c plus e plus f minus a minus d. Now let's first look at the sides of the initial quadrilateral. Take this plus this. We have that a and d cancel out here and here, and we get c plus e plus f minus b. But this plus this is exactly c plus e plus f minus b, and therefore ab plus ad equals bc plus cd. So we've got our first equation here. Let's think about what the second equation can be. Well, let's take AE plus EC. We have A plus D minus B here, and B here, so the B cancels out. Then we get A plus D up to here, plus C plus E. So A, D, C, and E. And if we consider this plus this, so CF plus FA, we get C plus E minus B plus B, the B cancels out, plus A plus D. So in total, we get E plus C plus A plus D from here, and from here we get E plus C plus A plus D again. Finally, let's take BF plus FD and compare to BE plus ED. Well, BF plus FD equals B plus C plus E plus F, and then minus A minus D, and this A and D cancel out. So we get B, C, E, and F. And what do we have on this side? Well, we have B, C, E, and F, exactly the same thing. So we got our three equalities that are true every time that we have a circle here. And it turns out that if we don't know if there is a circle here, but we do know that one of these three is true, then we can prove that the circle here exists. And the proof is completely analogous to the one that we showed a couple of minutes ago. This is the optional problem. We have a quadrilateral, and this is one of the diagonals, and this is the incircle of this triangle, and this is the incircle of this triangle. And we have to prove that the point of tangency of this circle and this line is the same as the point of tangency of this circle and this same line, if and only if the quadrilateral is circumscribed. And being circumscribed means that there exists a circle that's inscribed in the quadrilateral that touches all of its four sides. And if and only if means that we should prove it in both directions. If we know that this tangency point is the same, then there exists this red circle. And if there exists this red circle, then prove that the tangency point is the same. And here's the solution. First, I'm going to assume that the tangency point of this circle and this circle with this line is the same. And I'm going to prove that the quadrilateral is circumscribed. I'm going to denote this segment by A and this by B, and therefore this is B and this is B because they're tangent to circles, and this is A and this is A for the same reason. And also if this is C, then this is also C, and if this is D, then this is also D. And so this plus this equals B plus C plus A plus D. And this plus this equals B plus C plus A plus D. Exactly the same. And therefore for this quadrilateral, we have that the sum of the opposite sides equals the sum of the other two opposite sides. And such quadrilateral is always circumscribed. Now let's prove the other direction. I'm assuming that this red circle exists, and I'm letting the tangency point of this circle with this line be here, and the tangency point of this circle with this line be here at a different spot. And we're going to prove that this point and this point coincide. Now I'm going to label this as A, this here as B, and the little segment in between as X. So I will need to show that X equals 0. Now if this is B here, then this is B here because of the property of tangent lines from a point to a circle. And if this is B plus X here, to this point, then this here is also B plus X. This is A, and so this is A, and this is A plus X to this point, and so this is A plus X. If this is C, then this is also C, and if this is D, then this is also D. Now we have that there exists a circle, the red circle, that touches all four sides of the quadrilateral, and therefore we know that the sum of one of the pairs of opposite sides, this one and this one, equals the sum of the other pair of opposite sides, this side and this side. And therefore, C plus A plus X, which is this side, plus B plus X plus D, which is this side, equals B plus C, which is this side, plus A plus D, which is this side. And now we can cancel out some of the terms. The B cancels out, the C cancels out, the A cancels out, and the D cancels out. What doesn't cancel out is this X and this X. And so we get 2x equals 0 or x equals 0 as desired.